Hello. I guess I shouldn't expect someone to answer on the other side, but I believe we are now live. Thank you. First of all, thank you everyone for joining this panel on the security evaluation of state-of-the-art zero-knowledge systems. Thank you to the organizers for this incredible ZCon 2 Lite conference. And today we're going to be talking about a very important issue that is sort of more reinforced in the past few years, right? So we know that in state-of-the-art cryptography in general starts in academia, in an academic environment with papers and schemes that are being built to find and proven security. And then there is several of these schemes that throughout the years have gone into kind of an implementation and have been put into software in order, in many cases, to be deployed in real systems, right? And of course, we're here talking at the Zcash Foundation conference, and Zcash is one of the perfect examples for how to ensure that some academic work, paper, or protocol that is designed is actually being implemented and deployed secured, right? And we know that many times sort of there is a little bit of a gap because not always academics care about the implementation and not always developers know how to understand or interpret the security of those schemes, right? So there's these kind of two sides of the story, and we want to explore this today. So we're going to really just start with a bit of an intro by each one of our panelists. I will let them do the intros, it's nicer. And also, if you can, please add just a few words of what do you think is the problem, or what, in short, where do you think is the main challenge there? Maybe we'll start with Mary.
Hi, everyone. I'm Mary. I currently work at the Ethereum Foundation. I am originally an academic. I did a PhD in cryptography at University College London. And generally speaking, I have been looking at zero-knowledge proofs, and in particular, how to implement zero-knowledge proofs which have setup ceremonies, or zero-knowledge proofs which are universal in nature. So the setup ceremony is a lot easier to run, maybe can be used across many different applications. When it comes to implementation work, I haven't done as much, but I have done some work using Artworks, which was written by Pratiusz. Also, I have actively been involved in reviewing the Grot16 setup, which was used for the current implementation of Grot16 by the Zcash Foundation, and in particular, just making sure that all of the additional elements which they're giving out in the setup doesn't impact the security of the Grot16 prover.
Pratiusz?
Hi, everyone. I'm Pratiusz. I am a PhD student at UC Berkeley. I work on applied cryptography generally, and specifically, I guess relevant to this conference, I work on SNARKs. I worked on, I guess, a number of papers on SNARKs, and I'm also a co-author of the Artworks SNARKs library that Mary mentioned, which contains implementations for a lot of SNARKs, as well as basically the entire, all the components that you would need to implement a SNARK. So I guess, I have a little bit of experience on the implementation side. So I guess in my opinion, like the biggest challenge is just that there's lots of moving parts in SNARKs. Oftentimes these moving parts aren't specified by papers, and they probably shouldn't be, because you don't want to, that kind of detail doesn't belong in a academic paper. But sort of going from that high level description to something that is implementable and secure is challenging, and we need to sort of figure out the right abstractions and techniques to make sure that translation happens securely. And right now we've only done it via like very careful manual auditing, and maybe we should try to figure out simpler tools to make that a bit more easier.
Yeah, go for it.
Hi, I'm Eran Tromer. I'm a cryptography researcher. I work on zero-knowledge proofs and their applications, as well as other things in the realm of security and privacy, like side channel attacks and operating system security. And among the applications that I found for zero-knowledge proofs have been the protocol underlying Zcash, as well as other relevant components and various prototypes for systems that argue about how data flows, whether it's transactions or images. And I'm really excited that we are here today, broadly construed, at the point in time where this vision of zero-knowledge proofs, which was born in the mind of theoretical cryptographers decades ago, is finally living up to its claims and is meeting these very real societal needs for privacy and for creating trust. Unfortunately, this is where the difficulty also comes from, because those theoretical cryptographers on whose shoulders we're standing were very, very smart. They build amazing mathematical structures that have been elaborated on, our ability to understand those as laypersons, user of these systems, as well as experts, simply exceeds the current tools for understanding and building confidence. So if you study hard enough, you may be able to understand some part of the problem, and you spend a year, you can even formally analyze it with the right training, but what about the rest of the parts? And so it feels like we are all rushing forward to solve the world's privacy problem, as we should, but the foundation on which we are running is rickety.
Thank you, Eran and Mary and Pratish. That was a great introduction. I'll just quickly introduce myself and jump right away into the kind of first question or concept. So myself, I'm Daniel Benaroch, and I'm the Director of Research at Kedit. We're a company who have built privacy-enhancing cryptography tools for enterprise. And we're kind of taking also an interesting approach to the software. I'm also organizing the ZK proof effort for standardizing zero-knowledge proofs. And actually that could also come relevant in this conversation. So I'll try to keep the shilling to a minimum. So maybe let's start, Pratish, with you. A quick question, sort of, let's try to understand what is the process today. What happens today, kind of of the lifetime of the scheme or the protocol, from the moment it's like invented or created to the moment that it's implemented or actually deployed, right, as a software piece. And sort of what would you say should change in order to make that more robust, or could change to make it more robust?
Yeah, so no, that's a good question. I think it varies from paper to paper, but roughly the idea is that you have, you take a look at the sort of high-level description, which is not generally what you have in these papers, which can omit details like, what kind of, for example, if it's a elliptic curve-based protocol, it can not talk about what kind of curve to use. But so you go from like this high-level description, which just assumes some maybe abstract underlying assumptions, such as a pairing-friendly curve or just a normal curve or hash function or whatever. And then you have to go from that to actually, extracting from that an implementable description of the protocol, and it's filling in sort of these abstract parts that have been left open, and trying to fill them in with like secure components. And then when you translate that into code, and that's where you have, tricky things that come into play, like how do you encode stuff? For example, if you're using if your protocol uses a random oracle or is Fiat-Remy transform, then you need to figure out how to encode the messages that go inside the random oracle. If you need to transmit stuff over the wire for, because you're sending your transaction proof to the network, you need to figure out how to serialize the elements and deserialize them in a secure manner. And you need to sort of make sure that while you're doing this translation, you're sort of preserving whatever security guarantees you want from the protocol, which can be, it's not always trivial if you're not familiar with, what the authors had in mind originally. It might not be always explicit in the paper. They might assume some implicit knowledge. And this is just like in the implementation phase. And then in the deployment phase, before you actually take this, whatever you implemented and how to deploy it, you have to, double check that it's implemented correctly. So this involves audits, both internal and external. And And you have to make sure the team that you're hiring for the external audit is knowledgeable within the sub area that your protocol requires. So yeah, I think that these are the three main steps. Is that what you had in mind? Or do you want me to dive into detail on any of these steps?
No, this definitely sounds good. I mean, you've touched upon those three aspects, right? And there is kind of, if we want to get more granular, there are kind of gaps in between each of those, right? If we go from the abstract of like theory to applicate to practicality, now we brought it down to even a lower level, right? So maybe Eran and Mary, do you have anything to add there? What could be done differently in those sort of between the first kind of the paper to the first implementation and sort of from the implementation to the deployment, right? I mean, like.
So when it comes to the paper to the first implementation, I actually think that's quite a good question, because when people are implementing, they're always thinking about efficiency. They want to do everything as fast as they possibly can because they have an application in mind. They want to make sure that it's perfect. And actually, I wonder if this is not the way to go. So if you have a protocol which you're imagining lots of different people using, maybe it's got different purposes, maybe it's going to be deployed across different systems, then I wonder whether it makes more sense to actually start with a reference implementation, something whose sole aim is to be as simple as possible and to just define the protocol almost as pseudocode before you start trying to sort of say, I can do this optimization, I can do that optimization. Maybe if I put this group element there here into that different place, it will run just a little bit faster. Because every single one of those improvements you do make it harder to make sure that the protocol has been implemented correctly, harder to see this scheme as a whole, and harder to make sure that you've got things right. So I think having a initial reference implementation step before you go for the final, here's the protocol we're going to use, would make a lot of sense.
I mean, who's responsible? Sorry, go for it.
I'd like to chime in with an important hurdle that we actually seem to have mostly figured out. So the innovation most commonly comes from academia when it comes to inventing new schemes. And academia has an incentives problem. And most cryptographic schemes get published as academic papers, or as a student or professor, you try to aim for the competitive venues, you get your PDF accepted, everybody's very happy, you move on. Maybe you even did a crude prototype, so you can provide numbers in milliseconds, you make the reviewers very happy, and again, you move on. It's very rare to have the incentives aligned for academic researchers to create useful code. And by useful, I don't mean production ready. I mean even something that other people can run without cursing constantly. And while this has been a curse on cryptography as well as other fields of computer science for a long time, it looks like in zero knowledge, if you look at recent years, we seem to have figured it out. We have the incentive structures, partly through the magic of blockchain economics, partly through the dynamic the ecosystem and the norms that it has established, where quality code does get created, as well as the frameworks that enable that. So I was fortunate to have been part of Skipalab that created LibSnark, that was the foundation for implementation of many schemes. And now Pratyush picked that up and is doing amazing work with Arcworks and all of the schemes that are being prototyped on top of it. I'm very proud of our community for solving this one.
Yeah, this is a great point. And I mean, the three of you have kind of touched on this kind of small gap. And I want to dive with one shorter question, which is, who should be responsible for closing this gap, right? Should academics provide this reference implementation? Maybe, and of course not in every case, but maybe with those papers that are more have more chances to actually be implemented fast, which is quite a lot. Or right, I mean, as you said, Eran, in some cases it's the same implementers writing the papers, in which case it's quote unquote trivial that they will give that reference implementation. And that's kind of the ideal scenario. But in terms of academics, right, or should the implementers then take the paper and expect that all of the details have been written out or figure them out, right? I mean, academics also tend to take things as black box in this sense. So Should it be the community, maybe the conferences organizers imposing certain kind of submission criteria, maybe through standards? I mean, are there any thoughts on this?
I think there should be more of a focus on trying to get at least an initial, as Mary says, reference implementation that people can take a look at and sort of when they're going for optimizations, match up and make sure the behavior at least is preserved. I think to do this, we do need to sort of make it easier that for people to implement it. I think for a long time, like in cryptography, we didn't really have, like, either you have an implementation that works, or you have an efficient implementation, and oftentimes it's like difficult to reconcile the two without putting in like significant effort. So I think there needs to be a little bit more effort to make like a sort of toolbox that people can use, and we've been doing that in the zero knowledge community. And there's been, I think there's a lot of high quality implementations, not just I think from ArcWorks, but also from many other teams. I think extending that to maybe other places would be important, as well as maybe those kinds of schemes come into play. But yeah, I think getting publicity out there, like for example, not everybody knows Rust, right? Especially in academia. So maybe having Python wrappers which allow you to write a simple but still relatively efficient protocol, making use of Rust under the hood to get efficiency, right? So you get like a almost pseudocode-like implementation, but you also get performance, so that you can put that in your paper and be like, look, our protocol is very efficient. So I think that can help align incentives just by making it more usable.
Mm-hmm. Definitely.
I'm actually going to mention two things which I think make this very challenging. The first is sort of not necessarily a challenge so much as a comment saying that not every work that gets published necessarily should be implemented. Like, especially if we're talking about schemes which are still very much talking about asymptotics because they've not got efficient enough to be implemented, which would have been the case for zero knowledge 20 years ago. Writing in an implementation for those kind of schemes doesn't make so much sense. The other thing I would mention is that it is very common for cryptography researchers, I mean, certainly not all of them, but maybe as many as half, to not come from a computer science background. And this means that, especially if you're talking first-year students who wrote the paper, they may not code. So if you're sort of saying, okay, first-year students, you can't write a paper because you can't code, this might even be a reasonable thing to say, but there would need to be resources available for them to learn, I think.
Definitely makes sense. I want to maybe extend on this, Mary, and ask you also related to the talk you just gave. You were mentioning some of the security models, and the question is really sort of, how does proving security of these schemes kind of change or affect the security of the implementation depending on the assumption or the underlying security model more than assumption? And also sort of as an extension to that, why are kind of application protocols, especially really around zero knowledge proofs, harder to prove security of than like a proving system itself?
Okay, so if you're talking about, if you want to go for the most efficient things, why do those have more difficult security proofs? Is that the question? If it is, I can answer.
Well, you can take it as that if you want to. So, yeah.
Okay, it probably wasn't. I'm going to answer that one anyway, though. So a lot of the time, if you're trying to build a zero knowledge proving system, you would want to be reducing your assumption to something which you can actively break, something falsifiable. So if you wanted to say, I have security in my scheme, because if you can break my scheme, then you can also break the decisional assumption or something like that, then what you could always do is you could implement your attack. You could say, this is what my attack looks like, and I'm pretty sure that it works because I implemented it. So that would then give you some pretty good understanding that maybe your scheme is okay. If you're talking about more modern, more efficient snarks, often these rely on non-falsifiable assumptions, where if you're wanting to actually implement that break, it's not so clear how to do so. Like, especially in the algebraic group model, this does rely on the adversary having an idea of how it generated the group element. So you'd then have to model your adversary as having an idea of how it generated the group element if you were wanting to go with the same kind of audit approach, which maybe isn't so simple to do.
I
think there is the inherent difficulty of modeling and reasoning about the security of the underlying zero-knowledge proof system. But in practice, even greater challenge is that of expressing and reasoning about the security of the protocol that uses the zero-knowledge proof system. Precisely expressing the application level properties of something like the Zcash asset transfer protocol, let alone even more complex protocols that have been studied and are being built, is extremely delicate and fiddly. And even the original Zcash paper had an omission in its model of security allowing the Ferigold attack. So it was provably secure, yay, but was actually not even claiming, as it turns out, one of the properties that one would want. And that got fixed later, but then another definition came out that was even more general. And so clearly, even for something as simple as asset transfer, human grasp of the intuitive properties that one wants is on the verge of the capacity of even the experts. And as we build larger systems, how can we know that the specification that we provide really implies our intuitive notions of what the system should do? And this is so confusing, so insidious, that we often see people confusing themselves into believing that zero knowledge solves all sort of problems for which it doesn't actually make sense. For example, arguing that, oh yes, we'll prove that some witness exists that has all sort of properties, but if you look at it formally, you realize that of course such a witness exists. The question is there a witness for someone trusted, or witness related to reality, or some other additional criteria that the protocol actually does not enforce, and therefore the application level security crumbles. And the catch is that while we are working away to nice properties for simple standalone zero knowledge schemes, we are surely lacking in tools for expressing those of applications, and also in tools for building up proofs of those security, because the underlying components, like the simple ZKP schemes, are tricky to work with. The notions of composability are what happens when you put together several proofs with other components, things like non-malleability and simulation soundness. They're very finicky. And so we see a lot of things being suggested and deployed without these proofs, and maybe some of them are secure. How can we tell?
Absolutely, this is a very, very good point. And Pratyush, maybe do you have a bit of an overview of what tools exist out there to potentially help ensure, or if we could build, right, if the community could build, what tools would those be to help ensure the security in a bit more of an automated or formal way? I mean, for applications specifically, maybe.
I think, I'm not sure there exist yet good tools to prove, I guess, security of formally, I guess, formalize the proving of entire protocols yet. I think there's been a little bit of work on trying to like automate stuff in the UC model, but sort of UC is universal composability. It's a particular formalization that's used in cryptography, but that is in itself like a very, it's a pretty esoteric and pretty complex piece, sort of formalization to work with, which not all even cryptographers are familiar with. Just like another level of abstraction above standard like simulation based security or indistinguishably based definitions of security. Yeah, I don't think there's like we don't yet have good tools to sort of reason about security of, for example, snarks, like individual snarks. Like we don't have a sort of automated tooling to be like, here are my assumptions, here's the protocol, please, spit out a proof if this is secure, or like if it's insecure, please show me an attack. And I think we also do not have tools yet to easily reason about complex protocols which have a lot of moving parts, which and sort of assume these parts are secure, please give me a proof that the whole protocol is secure, or violates these XYZ assumptions. But I feel like even just the act of trying to maybe do that can help improve the paper proofs, because it forces you to clearly lay out or specify the assumptions that you're making and the properties that you want out of your protocol, which oftentimes, like, you're in the rush to write a paper and you might miss a particular thing. So hopefully, if we get these tools in the future, even if they're not efficient, they can just help us improve the paper proofs directly. Yeah.
You mentioned, go for it, Mary. Go for it.
I guess one of the challenges is that actually even defining what it means for these applications to be secure is really complicated. Like, definitions are often one of the hardest parts of papers. It took years for people to even get the definition of a zero knowledge proof correct. So when it comes to defining what does it mean for my somewhat sort of fuzzy looking scheme to be secure, that is something which is likely to be quite scheme specific and possibly quite complicated.
So you all mentioned also this idea of the requirements, right? I mean, I guess there's kind of two main approaches for potentially proving the security of a generic or a protocol that is composed of several sub-protocols or sub-schemes, right? Cryptographic schemes. And of course, there is also a bit of a conversation on the Discord around the fact that we need to, ensure the security of the individual components by themselves independently. But then there is kind of this layer on top that has to have the definitions that you were all mentioning, that it captured kind of this global picture, right? And how these components come together. So there is, of course, the notion of composability and universal composability. Now, is universal composability enough? Do we need to have also sort of these other definitions like indistinguishability of the ledger or non-malleability? Do we have any way of ensuring that if we have these four, for example, I think in the sapling protocol, the security was of indistinguishability, non-malleability, balance, and spendability. And then I'm wondering what you think, if this is sort of enough and we can be assured that this is secure, for example.
I mean, a correct UC security proof would probably be enough, but then you still have the problem of writing your functionality such that it accurately represents your model. And that, again, is going to be scheme specific. So it's sort of, in a way, it removes the problem of how do these different parts interact. Can maybe my signature here break my encryption scheme there? It removes that worry. But the worry about how do I know that what I'm proving is even the thing I should be proving, I think that just gets moved to a different place. It's still there.
So there on Discord is pointing out that this is all doom and gloom. So let me say two positive things about our ability to verify things. So first, as Deora rightly points out, we actually have a lot of proofs for parts of the protocols, namely optimizations. You can show that if some less efficient protocol is secure, then some more efficient one is still secure because, well, maybe you permuted and rearranged your Peterson bits for efficiency, but you can formally prove a reduction. If you could break this, you could break that. And so it's as secure as that. And that means a lot of the complexity can be shed away through these very local reasonings that do not require complicated modeling and composability arguments. And then you remain with a smaller, simpler protocol to prove. Another thing that we have running in our favor is the fact that some properties that are very important are also easy to prove. For example, the zero knowledge properties of zero knowledge of the basic zero knowledge schemes are typically much simpler to argue than the soundness of zero knowledge properties. You basically add some randomizers and you argue that they are random looking in a formal sense. It's the warm-up exercise of the formal proof. And that to an extent also holds for the larger protocols. You can show that some kind of privacy properties follow from the zero knowledge properties, as well as things like pseudo-randomness of hashes or random oracles. And so getting convinced of privacy, at least at the transaction level, I'm not talking about the network level, is something that we can get, it's easier to get confidence in. And that's actually crucial, because remember, the systems that we're building have two different kinds of failure modes. There's soundness failure, where the system fails to enforce something and money gets created out of thin air, or your money gets stolen. And then there's a zero knowledge failure or privacy failure, where people can learn about your transaction. And the former kind, the soundness failure, integrity failure, that kind of thing, you can sort of stay on the ball, and if you're even if there's a vulnerability, if you're fast enough in mitigating it, maybe you'll save the day. And that's exactly what happened with Zcash Sprout. The internal process within ECC recognized the issue, which was mitigated in time, universe saved. Whereas with privacy, you don't have that privilege. If you leaked information out there on the chain, it's there, and then you cannot erase it. And if people will find a way to extract and exploit it, then they will figure out who you paid when you were 14, and that gets embarrassing. So the fact that we can prevent the latter by relatively simple arguments is something that is important to keep in mind as we build this for deployment by users who are often risking themselves or their future selves by broadcasting their financial transaction or trusting us to make sure that they're protected.
That's a very good explanation. I think there is also agreement in the Discord chat, which is a good thing. That the public, the audience agrees with what we're saying. And you mentioned, I guess earlier, both the Fair Gold and now the kind of the BCTV14 vulnerability that was found in Sprout. And sort of there's a question here of how could we as a community prevent, actually publishing the papers with those problems, or implementing them, or how do we catch them? And then there is a kind of maybe a bit of a controversial question that is, would in that case sort of proprietary code, be better because the whole vulnerability is not exposed, or would you would still want to have the open source and risk someone actually find it and sort of change? Anyone would like to give a shot?
I think especially in the blockchain context, I think proprietary stuff is just a no-go, because eventually it has to run on somebody's machine, right? Which is not controlled by you, just because that's the nature of these decentralized systems. So I feel like if you try to hide it, then somebody will be even more motivated to go in and look and try to maybe reverse engineer. And then you won't even, you might have some false sense of security or confidence in the security of your process, right? Security by obscurity has almost never actually helped us in the long run, right? It might help us in the short term, but I think generally, I also feel like one positive side of the fact that these schemes are so complex is that finding an attack on them can also be a task that not everybody can perform. So it's sort of like a curse and a blessing. So I don't feel like anybody would have been able to find this. Most people will not have been able to find, for example, the BCT14 bug and exploit it, right? Just because that requires knowledge of, you have to read the paper, read the implementation, double check that, this assumption is being violated, and then try to actually exploit it. So yeah, I feel like I think in this case, open source is actually better, because it allows people to, people who are not on your team, who might be on your site, to actually go in and take a look and audit your code and then publish it. So proprietary stuff, you can't then do that, and motivated attackers can. So.
If we're talking about decentralized applications specifically as well, if you're sort of saying, here's my closed source piece of code and I'm not going to tell you how it works, but please store all your money with me, then that becomes very easy to insert backdoors, which means that you can print money and it becomes very hard for people to verify that you've not done this. So, I mean, I don't like security by obscurity in any context. I think very few security researchers do. But I think for this particular context, it's even more nonsensical.
I strongly agree. Security abhors closed source. And this is another dynamic that makes the difference here, is that in our kind of market, there are relatively weak incentives for scrutiny and auditing of closed source. It's just too high, too easy to prioritize shipping things and to cut corners on the audits if no one else sees what you're doing. It's not like there's a government contractor that will demand to have the audits and have the capacity to verify them. And whereas with open source code, it's the converse in our community, because there are so many people who whose eyeballs are honed for vulnerabilities of all sorts. So you have the mathematicians and the experienced programmers poring over codes, and the resulting responsibility that it instills on the programmers serves as a deterrent for nefarious activities, but more mundanely, just as an incentive to make the code pretty understandable and therefore probably safer.
This is important. I'm actually glad that we're going to be making Kerit's code source also open source, so I won't have to deal with that obscurity either. So we've been talking a lot about this gap that is kind of straight away, right? Like from the theory to the practical, and in some sense, we're trying to think about what happens when we start deploying these cryptographic systems, specifically zero-knowledge proofs. But then there is the question of kind of mainstream, right? From deploying it and having, a set of, sort of small set of people understand what's going on and ensure the security, you have the larger kind of set of the public who would like to understand or at least know or trust the security of the system, right? Like not have to dive deep into the mathematics or something to understand things, and probably just take it as a black box, but still be insured. So what can we do as a community? How can we ensure that the progress of security evaluation goes along with kind of the mainstream adoption process, right? Can we use standardization processes, or can we work with conferences in specific ways? I mean, go for it, right? This is an important question.
So clearly there's a need for communicating what we do, why it works, and why it can be trusted. And there's a lot of educational effort coming from all directions. I mean, we've seen Vitalik writing wonderful blog post tutorials to why zero-knowledge proofs works for several different schemes. We've seen some people in academia like Yuval Ishai writing blog posts and even whole books. And I think the largest effort in this direction is the zero-knowledge proof standardization effort. Proper disclosure, several of us here on the call are avid contributors. For those who haven't seen it, it's a series of workshops accompanied by an editorial document production process that has a lot of in-workshop interactions on real-time education, but also written deliverables like the zero-knowledge proof community reference, which is a lengthy tutorial that introduces the notions of zero-knowledge proofs and the important constructions, they properly contextualize, and has discussions of different applications and how to evaluate them. It's a living document. If you haven't seen it, go check it out and please contribute. And I think that's this kind of outreach, just putting the hours into distilling hard-earned intuitions into prose that is targeted at the audience is the way to achieve it. I think that compared to the complexity of the concepts we're trying to convey, we are also being pretty successful in convincing the world that this kind of weird moon math is a viable path to building privacy and trust in decentralized systems.
Barry or Pratish, you wanted to?
Yeah, I think, yeah, I agree with sort of this education effort that has happened. Like, I think when I started my PhD, even then, like zero knowledge proofs were some sort of, you know, as Iran said, these magical objects, moon math that, you know, you plug stuff in and then you have privacy and scalability and succinctness and all kinds of nice properties. But I think since then there's been actually a lot of effort from within academia and also I think outside academia to educate and spread, you know, understanding of how these things work. And as a result, we've seen a lot of people with maybe not even a formal cryptographic background come into the space and contribute and you know, develop new schemes, develop new applications, which sort of helps with our, you know, you get more eyeballs on this kind of stuff, which helps with our confidence in these things. And yeah, I think as part of this, as some of these things are like, as Iran mentioned, the ZKP proof workshops has been excellent. You know, podcasts, the Zero Knowledge podcast and the Associated Study Club and sessions and Summit and so on. I feel like that's one really, I think, in my opinion, unique thing about the zero knowledge space compared to the rest of cryptography, where I feel like we don't really have that sort of industry, I guess, public outreach and industry engagement. And as a result of that, I think it's improved the research side as well. There's, you know, people strive to make their protocols simpler, not only for the sake of consumption, but also because it then helps with deployment and implementation. So for example, we have this modularization, which has happened with recent kinds of snarks, where you have polynomial commitments plus these polynomial IOPs, which are, in my opinion, much simpler to understand than some of like the QAP-based snarks. It's like much easier to reason about why the different parts are secure. Yeah, I think we've done a good job. I think we definitely do better in trying to make the math more accessible. But I think we're miles ahead of a lot of other cryptographic subfields.
Mary, would you like to say some final words on this topic before we wrap up?
Yeah, I mean, mostly I'm in agreement that when it comes to making sure that people are okay using moon math, so to speak, educational resources and making things accessible means everything. Like, I mean, to use an analogy, I don't know how my car works. I drive it everywhere. I have no idea how it works. So, but if I wanted to, I know that I could spend, I don't know, the next number of years reading references, finding reading material, internet material, online videos, teachers, etc., in order to learn how that works. Like, I don't see a situation where I come across a barrier and can't get past it, and there's no one that can help me past it. So I think that when it comes to the zero knowledge space, giving people the same reassurance that even if they don't understand it, if they really wanted to, if they put enough time and effort into it, they could understand it, goes a long way.
Thank you. Thank you all. So just to close, because I think we have like two minutes left. What would be the one thing that you would tell either academics or developers in order to help in this challenge? And you can be extreme if you want. Quick answer by maybe Iran.
So I would tell them that this is one of the most exciting and productive areas in computer science nowadays, with an amazingly short bridge between cutting-edge theoretical research and real-world applications. It has some of the brightest and most enthusiastic people as members of its community, eager to hang on your word when you solve their problem. It's a great way to make impact. And it touches upon many related areas like formal verifications and fascinating abstract questions in modeling randomness and random oracles and the elliptic curve properties. So I feel we are fortunate to be here at this time when so much is being built, and there's so much opportunity to think up amazing, elegant math and see people actually using it next year to solve real-world problems. It's rare.
Thank you. Thank you, Evan, for those last thoughts. And I believe that they echo what we all think in this room. Thank you again, Mary, Pratush, and Evan. This was a very exciting panel. I think I thank also the Zcash Foundation and organizers for inviting us. So I hope you all enjoy the rest of ZCon 2 Lite. Bye.
Thanks, everyone. Bye.